So in this video, we're going to go through an example here of finding an other average power dissipated through the resistor. Now I'm going to go ahead and do this using two methods. The analysis is going to be the same in both cases. Let me make sure that I label those as both volts. What I mean by the analysis in both cases, I'm going to use two formulas here. I'm going to use the power is 1/2 the real part of the voltage times the complex conjugate of the current. But I'm also going to use 1/2 I sub m squared times the resistance. Okay, so I'm going to do both there. The reason I like this formula personally is this formula, I don't ever have to worry about, making a mistake with it. It always, quote, works. So to do this here, the first thing we should do is, of course, convert this 10 at an angle of 50 degrees to polar. So 6.43. So this is going to be 6.43 plus J 7.66 volts. And then this 5 at an angle 0, we could go through the same thing, and this is just 5 plus J0, so it's in other words just 5 volts. Now I'm going to do two current loops here. I1, I2, and then I'm just going to define my current through the resistor as going down. Doesn't really matter if you define it going down or up in this case, but I'm going to define it going down because I like to, because ground is at the bottom here typically, and so I like to think of it as going down. So the phasor current that I'm looking for, I, is going to be equal to I1 minus I2. So of course I'm going to have to find I1 and I2. So I'm going to have to write some loop equations here. So let's look at loop 1. Well, this arrow comes into the negative side, so I'd have negative parentheses 6.43 plus J 7.66. I'm not going to distribute that just yet. I'm going to leave it like that. Plus J45 I1 plus 2 I1 minus I2. And this is all equal to 0. Now, I'm going to go ahead and move this term to the opposite side because that has no variables in it, so that's why I didn't bother distributing the negative. And then I'm going to combine some like terms here on the left side. So my equation boils down to 2 plus J45 I1 minus 2I2 is equal to 6.43 plus J 7.66. And that's loop 1 equation. Well, loop 2, I'm going to have to go kind of back and forth here a little bit. Let's go ahead and start with the voltage source again. So I'm hitting the positive side of that voltage source. So I'd have 5 plus, then I hit this 2 ohm resistor, 2, in this case because I'm in loop 2, it'd be I2 minus I1. And then I could do plus, but it's going to be a negative J100, so minus J100 I2 equals 0. Now again, combining like terms and moving some things around here, I get minus 2 I1 plus parenthesis 2 minus J100 I2 is equal to negative 5. And so I have my two equations here. I have my two equations, 1, 2, that I would use, and I could use the calculator on the internet that I put a link to, this matrices calculator right here, to do it. Or if your calculator can do complex matrices, you can do that as well on your calculator. So let's go ahead and go back here. So when I did those computations, I got the following. I1 equals 0.174 minus J 0.135, and I2, this is in amps as a side note, I2 was 1.77 minus J 46.6, and that one's in milliamps. So let me go ahead and maybe write this one in milliamps too. 174 minus J 135 milliamps. So that they're both in milliamps. Okay, so then we can go ahead and compute what I is going through that 2 ohm resistor, because we said that I, if we go back up here, remember I was I1 minus I2. So I is simply 174 minus J 135 milliamps minus 1.77 minus J 46.6 milliamps. And so if we do that, 174 minus 1.77, whoops, 172.23 minus J, and then it's going to be a double negative here, so it's 135 negative plus, what was that, 46.6 minus 88.4. milliamps. And so now we're going to, again, do this 2 different ways here. So the first way we're going to do this, so at this point, no matter what technique, and when I say what technique, no matter what formula we decide to use up here, the analysis up to this point would be the same. Nothing different. But at this point, we're going to do 2 different options here. We're going to look at doing this by doing the 1/2 real part of the voltage times the complex conjugate current, and it's the other one. Now, what's nice for us is that the voltage is simply just 2 times this. So the voltage would just simply be, let me just do this real quickly on my calculator off to the side here. $344.46 minus J 88.4 176.8. This actually would be millivolts, because I haven't multiplied it by anything that would change it from milliamps to like volts, so it's millivolts actually. And so my power would be 1/2 the real part of my voltage, 344.46 minus J 176.8 times the complex conjugate of my current, which would be 172.23 plus J88.4. And this I should maybe emphasize, that's millivolts, milliamps. And when I do that computation, I get 1/2 the real part of essentially 75. It was 74.955, but it's going to round to 75. And remember, we already did some approximation when we had to convert that first voltage an angle of 50 degrees. And so I'm going to do 75 divided by 2 then, which is just 37.5. And actually this is, I'm sorry, I forgot my units here. This is milliwatts. Milliwatts. Okay, so that was one technique to find the average power once we had the current. Now let's go back to the current here in polar form, which is 172.23 minus J88.4 milliamps. Let's convert this to polar. And if you convert this to polar, you get that the current is equal to 193.6 at an angle of negative 27.17 degrees milliamps. Now my other formula here we had was this one right here. And I sub m is this term right here. Remember, that's my I sub m. So I could do the power is equal to 1/2 I sub m 193.6 milliamps squared times my resistance, which if I do that, we get 37.48 milliwatts, which is, if we round this, 37.5 milliwatts, which is the exact same answer that we got above. So, two ways to do this, but what I want to emphasize is no matter how we compute the average power, we always start off by just doing the same circuit analysis that we've always done. There's nothing different about the circuit analysis that we do. So that's kind of important to recognize here.